right, good afternoon, everyone. Welcome to this edition of our Electrical Engineering Pioneer Series. I'm very happy, delighted that you're all here to celebrate our own pioneer, Professor Jerry Mendel, today. So today is also Cinco de Mayo, so additional reason for Fiesta. So as you all know, this Pioneer Series was started last year to sort of both as a way for recording the history of our department in a way through the contributions our colleagues have made and to bring us where we are now, but also to sort of celebrate the individual accomplishments of our colleagues. And sort of today it's a fitting day to celebrate our colleague Jerry. So Jerry came to us in 1974. He's been here for more than 40 years. His technical accomplishments are vast in many fields of electrical engineering, in control systems, in estimation theory, and in seismic signal processing, statistical signal processing, and more recently in the broad area of computational intelligence, particularly in fuzzy inference and fuzzy systems. So naturally, he's won a lot of accolades and awards for his contributions to these fields. The other important thing that Jerry has done is serving as a mentor. His students are, in fact, at the top of our field. In fact, many of you might have listened to Professor Giannakis, who was here recently, who just received the free award, the top award in signal processing, was Jerry's student, and many others who are in the field doing their own excellent things. Even today you can go see, if you walk by Jerry's office and students sitting, they have this nice way of sitting next to each other and working through problems. It's very inspiring, actually, to watch that. So the format of today's, presentation, Jerry is going to share his thoughts and his journey, as a slice of it, so that, we'll record this and make it available for all of us. Followed by which there will be sort of this sort of conversation with a colleague, and we have Professor Keith Chubb today being the conversation is with Jerry, and so I don't know what they're going to talk about. Hopefully, it will capture very interesting things, and again, this will be archived for our. And of course, we will end the day with a reception, and I hope you'll all stick around for that too. So, without taking much of more time, I want to invite Jerry here over to the podium, and and ask him to share his thoughts with us. Jerry, thank you so much.
Thank you. Well, thank you for inviting me. I feel like I'm giving a talk at my own wake. I thought long and hard about the content of this talk, and what I'm going to do is I'm going to take you sort of through a very focused, guided tour of my more than 50 years career. And what I want to begin with is put what I think my viewpoint on research in perspective. I view research as synonymous with exploration. I think there's a certain excitement that we have when we do research, and an explorer travels into the great unknown, hoping to find something really new. My hero, actually, is Teddy Roosevelt. Roosevelt was an amazing person. I've read numerous biographies, and he took one of the most insane trips you can ever imagine down a river called the River of Doubt. He was totally unprepared for this, but somehow he survived. But what excited him was instead of taking a trip down a well-explored river, he took this trip down a totally unexplored river. And I think that's what research is about. So imagine being, how do I get this right? Imagine being an explorer on either the Delta in the Amazon or the Ganges Delta here, and you have all these choices, which path do I take? Do I just go down one? Do I branch out? Do I come back? How long is it going to take? How much time do I spend on each of these? You can can see there's a lot of math here. And these are all open-ended questions, and that's what we have in research also. For the most part, they're open-ended questions. And I was thinking, the journeys of the great explorers were underwritten either by nobility or by some society. Research takes a lot of time, and I want to begin by saying I'm very fortunate and thankful to my wife, who's here, Letty. She's been my royal underwriter, namely for underwriting the time I spent doing the research. I think everybody here who does research knows we spend a lot of time on this stuff. So just as in exploration, in research, it's important and arguably crucial to focus on asking the right questions. So in this short talk, what I'm going to do is focus on some of the questions that either I've asked or my students have asked, so you get a good sense of what I mean. So I want to go all the way back to when I was in graduate school, my first publication. We have sort of a fond attachment to that first publication. It may not be that important, I don't know, occasionally I think about it. I even found the notes that I kept for this one. I was going through my filing cabinet this week and I found it. Oh my God, I haven't seen this in 15 years. It really wasn't that important result, but thinking about it, I got a lot of satisfaction from it, and it sort of gave me the courage to explore further. So in 1962, I was in my PhD program at Brooklyn Polytech, and I was a control systems major in EE. I transferred from mechanical engineering into EE. And in my first course on control systems, and this is probably true today also, we learned something about natural frequency and damping ratio. So for those of you who don't know what that means is, think about riding a car. If you hit a bump or a pothole, you don't want the car to go up and down and vibrate. It'd be pretty sickening. You want a nice smooth ride. And so damping is one kind of a measure of that. So I had learned in a control systems course that damping was measured by something called this damping ratio, which is the logarithm of the ratio of two amplitudes that are separated by one period. That's called the log decrement ratio. So, as a graduate student, the following questions occurred to me. I said, why this ratio? Right? Is it possible that there are other ratios that could also lead to this same formula? And so what I did is I examined those questions, but not for amplitudes of single points, but instead I looked at ratios of areas. Right? And so area 1, area 2, so that area over that area. This was my favorite one, these triangles. And I found that they all led to the same formula. Right? So there was something inherent about this system that all these area ratios led to exactly the same formula. So actually, this was my first, this is a short article, probably a correspondence in the IEEE transactions on automatic control. Again, it's not terribly important, but it was fun. It gave me sort of a sense of excitement and that I could actually do something and get it published. So after I got my PhD in 1963, I came to Los Angeles and I worked for the McDonnell, well, it then wasn't McDonnell Douglas, it was the Douglas Aircraft Company in the Missiles and Space Systems Division. In fact, one of my colleagues, David Vaughan, from those bygone days, is here. Dave, where? Oh, good. Thank And I spent 11 years at Douglas before coming to USC, as you heard, in 1974. Now, some might not think that what I'm going to say was really lucky, but I never worked on a real project or real system while I was there. For 11 years, I worked on IR&D, independent research and development, which gave me an opportunity to do research that, looking back on it, was the same kind of research we do here in the university. That was a very special time, I think, in the history of the aerospace program and maybe engineering in general. The government was funding people and companies to do this kind of research. So again, there's a lot of luck involved in being there at the right time in the right place. In fact, my first assignment was, I was given 1 year to survey biological principles that could be used to design control systems. Imagine being given 1 year to do something like that. I was really fortunate. And as part of that, I came across reinforcement learning, homeostasis, learning control systems. There was no field called computer science then. I mean, pattern recognition, cybernetics. These were all things that I surveyed. And looking back on it, that study, that 1 year, really informed and influenced a lot of what I did in the rest of my career. Again, it was very lucky. So I worked on, over 11 years, you can imagine that you work on quite a few projects. You don't get as much time in industry to work on these projects as you do in the university. I could never understand how my friends, I was very friendly with Len Silverman, in the Control Systems Society, very active together, and he'd tell me, oh yeah, we're working on linear systems for 10 years. I'd look at him, 10 years? I said, wow, that's something. And then I came and I became a professor, and I realized, yeah, you can work on things for 20, 25 years. It goes by like that. So, I'm only going to mention one project that I worked on, and gee, David, you might have been my supervisor at that time. You may recognize this one. So I was wandering around the research building at Douglas, and I observed a couple of my colleagues using what I'll call the twiddle technique for design. Okay, so let me explain what I mean by that. They were designing the control gains for a missile control system, and they were adjusting two control gains, and I think there was a time delay. They were doing this trial and error by hand, and I think it was on some kind of an analog computer, because in my mind I can picture the paper streaming out. It couldn't have been digital. And this was a very high-performance system. It was a missile, and it was non-linear, and it had a time delay. So I asked them, what are the performance goals? What are you shooting for? And why are you doing this by twiddling? So they told me that the missile was being controlled by thrusters. Okay, that's stuff that's coming out. That's the fuel that's being expelled. And you could turn the engines on and off. Okay? And you might want to do that to conserve fuel so you reach the target. But they wanted the missile to fly in something called a limit cycle, okay? So you can imagine maybe this thing was going like that. I don't have any technical pictures of a limit cycle. So they explained to me that the key to a successful design was to know when to switch those thrusters on and off. And that happens at what's called the limit cycle switch points. And those are measured values of position and velocity for the missile. And knowing when to switch the thrusters on and off is very important because the missile only carries a limited amount of fuel. So you want to conserve that. Additionally, they wanted to keep the amplitudes of this limit cycle small, and they wanted the period to be as long as possible. They'd like the engines to be off for as long as possible. Okay. And then they told me that it was impossible to achieve best performance for all of these simultaneously. If you improved one, you worsened the other. And so there's a real design trade-off. And that was the first time that I had encountered this kind of a thing for a control system. And so finally they told me that the only way that they could work out a good design was by trial and error, which is what they were doing. So the question that occurred to me was, can this be worked out mathematically? So somehow they let me work on this problem for a year. I didn't have a supervisor there. And it turned out that what I discovered is that, yeah, you could work the whole thing out mathematically, but it had to be done in 2 steps. The first step was you had to express all the performance metrics, conserving fuel and the amplitude of the limit cycle, in terms of those switch points. The second thing is that you had to design the control gains in terms of those switch points. Okay? Now, this was a complicated system. It was non-linear with a time delay, so you had to be very careful that the system didn't go unstable. Okay? So after you went through and you realized it was this 2-stage process, the approach then was to specify the desired performance. Okay, they had the performance specs. That would lead to the coordinates of the limit cycle, which would then get mapped into the control gains. Okay? So it wasn't the obvious kind of an approach where you twiddle control gains, which is what they were doing, and observing the performance. It was backwards. Start with performance, and then get the control gains. Now, I only mention this long story because what I realized that, again, I'm looking back, and this sort of illustrates a trait of mine. I think my students are familiar with this trait, and that is that I like to observe experimental results, focus on interesting or surprising ones, and then explain them mathematically. Okay? So that's all I'm going to say about my 11 years at McDonnell Douglas. That was compression. And as Sri mentioned, I came to USC in 1974. I had a friend, George Saritas, who was a professor at Purdue University, and we were very active in the Control Systems Society. And he went to NSF as one of these program rotators. So he was in charge of the Control Systems program. So I called him up and I said, George, I said, how do I get a grant? He said, oh, you can't get a grant. You work at a company. But what you could do is you could write a proposal with a professor at the university, go through the review, and if it gets funded, go on a leave of absence. So I did that with George Becky, and we got the grant. And then I came to USC, and at that time, the department chair was Nasa Nahi. And I made it clear very early on that I wanted to stay. And without going into all the details, he said, yeah, that's good. However, we have enough controls people here. We don't need another controls person. Find some other area to work in. So in 1974, for those of you who are old enough to remember, that was the year we had this big gasoline crisis. We were waiting on these long lines to fill up our gas. And so now he said, Jerry, why don't you look into power or, energy, something having to do with one of those. And so I looked into the literature, and honestly, I wish I could remember how I came across the field of seismic data processing for petroleum exploration. I've tried to remember it, I can't. So what I discovered is this huge area of geophysical signal processing for petroleum engineering, petroleum exploration. None of my colleagues even knew that that area existed, but it was big. And one of its problems that I spent quite a number of years on was called deconvolution. Okay? Decon for short. So what I want to do is I want to tell you briefly what that's about. So suppose you wanted to find whether there's oil offshore, let's say on Venice Beach. Okay? So what you'd like to do is to go under the surface of the water into the earth and look around. You can't do that. So instead, what petroleum engineers do is not petroleum exploration engineers, I have to be careful here, they send a surrogate into the earth. And the surrogate is a source of energy. See here. So one kind of source of energy is an explosion. Now maybe there are places still in third world where they do this, but nobody here would let them set off explosions, killing whales and fish and all other good things. So instead, the exploration industry invented some very clever sources of energy. One is called an air gun that sends in a big burst of energy. It goes down as a bubble. It's got a lot of pizzazz in it. And that goes down into the earth. And that goes down into the earth and it bounces around, and some of it comes up and is recorded on those hydrophones. Some of it keeps going. There's a lot of stuff going on. And the goal is to create a picture, literally a picture, of what's below the surface. Now this is an ancient picture. If you go on the internet, you'll find three-dimensional. And the exploration people now talk about four-dimension, where time is the fourth dimension. So there's a lot of challenging signal processing problems associated with this, because the energy doesn't just come back nicely to a hydrophone. It crisscrosses, and the picture you get is a mess. Okay? I wasn't concerned with the crisscrossing. I was concerned with the fact that as that energy goes down into the earth, it changes. The source starts to spread out and get blurred, and it loses its shape, so to speak. And what comes back, instead of being a crisp picture, is a blurred picture. And what you have to do is get rid of that blurring, and that's what deconvolution does. For the digital communications people here, there's an analogy between deconvolution and equalization. I'm not going to go into that. So it turns out that I was very fortunate to meet a man named Mendel Robinson, who is really the father of seismic deconvolution. Very nice and generous person. He got his PhD at MIT in the 1950s when Norbert Wiener was there. And he was greatly influenced by Wiener, and he developed an approach to deconvolution that was based on Wiener filtering. So, since I was familiar with Kalman filtering, I asked the question, can seismic deconvolution be performed using Kalman filtering instead of Wiener filtering? I still remember going to a workshop, might have been at Dartmouth, I can't remember exactly where. It was on power system control, and while I was there, I realized that deconvolution was not a filtering problem, but it was a smoothing problem, interpolation. And so, I'll never forget, instead of attending the sessions, I just went out into some lounge and I started working out the equations and stuff. And I'm sure all of you who do, you get into that mode and you just can't stop. You've got to keep pushing it, okay? And that's exciting. That's the joy of doing research. And so that was a very joyous moment for me. That moment of recognition and then sitting down and being able to work it out. So that was around maybe 1975. And my students and I worked on different aspects of deconvolution and modeling for reflection seismology for more than a decade. And one of my first students, John Cormilo, worked on many aspects of this. And I was a new professor here. I guess I really didn't understand at the time how closely someone is supposed to follow the work of the students. And so John never showed me all the details. He was real good at simulation, and the results really looked good, but I'd never seen any real analysis until he turned in his dissertation. And then I couldn't believe every chapter was like a little masterpiece, really brilliant. Because I don't work with my students like anymore like that, but now my father will work much closer. So continuing with the reflection seismology, in the late 1970s and early 80s, I created a research program here called the USC Geosignal Processing Program, and it ran like a mini center, and it had support from oil companies like Chevron, Unocal, Shell, Exxon, and some of the service companies. Schlumberger was a member also. The reason I mention that is because my students had to learn how to write papers for two very different audiences. I was an IEEE guy. I was still active in the Control Systems Society, and I published in the AC Transactions. So they had to learn how to write articles for the AC Transactions with information group. But they also had to learn how to write articles for the geophysical exploration literature. For those of you who work in interdisciplinary research, you know that that's a very humbling experience, very humbling. They're two very different audiences, and you have to learn how to talk in the language for both audiences. So that was fun for a while, and then the bottom fell out of the oil industry around 1983. And at that time, Giorgio Giannakis was my PhD student, and I'll never forget, he came to me one day, and I had a continuing program like people work in an area. That's how we work in areas for 20, 25 years. There's continuity, a flow from one student to the next. So he came to me one day and he said, Dr. Mendel, I can't work in this seismic area anymore. I said, why? He said, there's no jobs out there. I said, okay, so what are you going to do? So he went away, and he came back one day, and he said, well, there's this area that I found called higher order statistics. And that's an area where you use more than just the mean and the variance, because you're dealing with non-Gaussian signals. And so if you use more than those two, you have the possibility to do better. Now that's also when I first met Max Nikitas. Okay, Max was working in the same area, and about Max, the rest is history, as they say. Turns out that Max and I organized the first workshop on higher order statistics. You know, there's this word higher and higher order statistics, so from the very beginning, we decided that all these workshops would have to be at higher altitudes. Hey, why not? Have a little fun with this. So the first one was in Vail, Colorado. This is not Vail, that's Lake Louise, in the Canadian Rockies. And then we had one in the French Alps at Chambrous, and Lake Tahoe, and other high altitude places commensurate with higher order statistics. So as a result of Giorgio's work on higher order statistics, as well as some of my other students, spent another decade working in that area on different kinds of signal processing problems that used higher order statistics. So I'm going to state two of the questions that we asked, and mercifully for you, I'm not going to show you any details. I just have to say that we were able to answer these questions. The first question, actually Giorgio is the one who came up with the answer to this one, was the following. Can a system that has an input and output, is described mathematically, be uniquely described just from measuring signals at its output? You can't measure the input. You don't know what the system description is. You only know what the output is. But you also know that the input is non-Gaussian. So you know something about it, but you can't measure it. Okay? So turns out you can. There's a unique solution to that problem. The second question was also really interesting. I had a couple of students who worked on array signal processing using these higher order statistics. And the question that they looked at is, in array signal processing, can hardware be replaced by software? So you don't need as many sensors. Instead, let me put it another way, is it possible to use the spatial nature of these higher order statistics to replace the spatial location of actual hardware? And the answer turns out to be yes. Again, you're dealing with non-Gaussian. We actually got a patent on that. So, moving on, another former student of mine, Anantram Swami, was there in the 1980s, and he, Max Nikias, and myself put together a MATLAB-based toolbox on these higher order statistics. Originally it was called HiSpec, and then it was changed to the higher order spectral analysis toolbox, and it was marketed for a number of years by the MathWorks. And unfortunately for us, this profitability fell below some threshold, and now it's available on their website as freeware. So I went from the seismic into the higher order statistics, and Bob, you were there when this transition was happening. And then in the late 1980s, I was already shifting into fuzzy logic. It's amazing the pictures you can get on the internet. Fantastic, fantastic. So, but I have to tell you that in 1986, I was president of the IEEE Control System Society, and it was really a hard pill for me to swallow, fuzzy logic. Okay? At the time, I felt that fuzzy sets was some sort of a cult-like activity, whose leader was Professor Latvizadi from Berkeley. One of my students, who happens to be sitting here, Robert Popoli, Robert, you're raising your hand, he was very persistent. And remember, you gave a series of talks to my PhD students, and Swami and Giannakis were there. They probably were laughing in the beginning, but by the time you were done, nobody was laughing. They all realized that there wasn't anything fuzzy about the mathematics of fuzzy sets, regardless of what Bush said about fuzzy math. So the feeling at the end of Robert's educating us was that this was really a legitimate area to work in, regardless of that awful name, fuzzy. Don't get me started on that one. Now, before I explain some of the work that we did on fuzzy, I want to take a few minutes to mention something that even today seems strange. Okay? So let me begin by mentioning that those of us in signal processing know how important linear algebra has become. In fact, Tom Kailath received the IEEE Medal of Honor for pioneering this work. So I think it's fair to say that linear algebra is the bread and butter mathematics for a huge number of signal processing techniques. There are many linear algebra methods, and they're all solved on digital computers using what I'll call standard numerical method. Whether that's, you go to MATLAB, MFly, it solves it. And today most people don't even worry about how's it solving it. They've done a wonderful job. In 1990, I had a student, Li Jing Wang, and he asked what to me, even today, is a very out-of-the-box question. That question was, can linear algebra problems be solved by means of training, like in a neural network? Okay? And he had the uncanny ability of taking problems and seeing some kind of a layered architecture about them. Not only for linear algebra, but for other kinds of problems as well. And once you recognize this layered architecture, you can then formulate the solutions as a training problem. And so again, he asked, can linear algebra problems be solved by a training procedure? And he showed that the answer was yes. And he did this for a lot of linear algebra problems. We published this in a number of journal articles. I'm going to get a little technical, so that you'll stay with me. Okay. So this was for LU decomposition, matrix inversion, QR factorization, singular value decomposition, symmetric eigen problem, Schur decomposition, solving linear equations, and solving Lyapunov equations. All those can be solved by training, in which each of these methods or problems has a unique layered architecture, and what you do is you train by applying unit vectors. So not only did he demonstrate this by simulations, but he proved mathematically that by doing this you would converge to the correct solution. So to me, even today, that was a very out-of-the-box kind of question. He's also the student who really got me deeply involved in fuzzy sets and systems. So you may or may not know this, but one of the powerful things about a fuzzy system is that it can be created by first extracting rules from experts. So you can convert expert knowledge into mathematics, and then you can program that, and that expert knowledge can then be used to help you solve a problem. Li Jing was the first to ask the following question: can rules be extracted directly from data? Okay, that was very different than what anybody was doing at that time. And he developed an extremely simple way for doing this, and in fact our 1991 paper is my most widely cited paper. So when I look back at this point, so now we're in the 1990s, on the kinds of problems that I have worked on from the 1960s through the early part of the 90s, most of them involved random uncertainties and reducing their effects. And I found that standard fuzzy sets were very limited in doing this. I mean, as funny as it may sound, there's nothing uncertain about a fuzzy set. It sounds strange. And so we segued from the standard fuzzy set into a more advanced fuzzy set that's called a type 2 fuzzy set. Some people might call it a fuzzy set. Okay? So Mel asked me if I was going to explain fuzzy. He didn't know, but the answer was yes. Okay, so let me give you a very simple explanation of the difference between these kinds of sets. So let me begin with a crisp set. So let's say you have temperature, and over some ranges, everybody is in complete agreement that the temperature is warm. So the degree of similarity to warm is 1. That's a crisp set. Okay, in this range it's warm, outside it's not warm. End of story. Oops. In real life, though, things are not as simple as that. There may be some region where everybody's in an agreement, but then to the left and to the right, people are in disagreement about this is warm. And so the similarity then to warm water tapers off. That's a type 1 fuzzy set. Moving up the food chain, people may not be in agreement on the span. What are the endpoints? There's uncertainty about those endpoints. So when you allow for that uncertainty, you get this green thing that we call the footprint of uncertainty. That footprint can be weighted in different ways. When it's weighted uniformly, we get what's called an interval type 2 fuzzy set. When it's weighted non-uniformly, we have a general type 2 fuzzy set. So now you're all experts on fuzzy sets. Okay, so it's the interval and general type 2 fuzzy sets that my students and I have been working on now for more than 18 years. So sometimes people ask me, well, how did you really get into working on type 2 fuzzy sets? So I have to let the cat out of the bag. I'm going to tell you a story now. It's a good story. I tell this whenever I'm at a conference and people want to know, and at a cocktail party, and usually nobody walks away from this story. I mean, you know, you tell someone, I'm an engineer, and they say, oh. You never want to tell anybody you're an engineer. Make up something. You never want to tell them an engineer, because you'll get, oh. So, in 1994, USC, and they probably still do, had a merit scholarship program, and there was a sophomore student named Matt Martin who was guaranteed that he could do research with a faculty person. Somehow he found out about fuzzy sets, and he came to me. He wanted to do research on fuzzy sets. So I had just written an IEEE Proceedings tutorial on them. I gave it to him. I never expected to see him for another semester. He came back a month later. And he wanted a project to work on. So we decided that the project would be, we wanted to write an article explaining fuzzy sets so that any high school student would understand what they are. Okay? Well, in order to do that, you need a good application, something that high school students will grab onto. So Matt was a very social guy, and he lived on campus, dormitory, mixed men and women, and so he goes back and he comes back and he meets with me, walks, oh, he said, I have it. I said, the quarterback, the USC quarterback, okay, he's got to make all these decisions. So what are the decisions? Well, does he pass? Does he hand off? Does he run? Okay. And there's a lot of uncertainty. That's associated that with fuzziness. Okay. What he didn't know is that I already had an application in mind. I wanted to see what he'd come back with. And the application that I had in mind, I mean, frankly, I didn't think football would be one that everybody in high school would be that interested in. Maybe guys, maybe small number of girls, but not everyone. But this one, though, I think would grab everyone. And the application was flirtation. See? Okay. It always gets a good laugh, but nobody says it. Now, the reason I felt that flirtation would be interesting is because of the well-known adage, I'm getting mixed signals. Okay? If you've been in that situation, that means, here it is, okay? One indicator may be telling you, yeah, there's a lot of flirtation going on. Another may be telling you, maybe there's none. I don't know what's going on. Somehow we're able to aggregate and arrive at, call it a level of flirtation. And so the reason that I like this is, okay, maybe I could think about rules in terms of indicators, and in our mind, we observe these indicators, and we are processing these rules, and if different indicators are firing different rules, somehow we're able to aggregate. Okay, and I can express that all mathematically using fuzzy sets and fuzzy logic. Matt liked this application a lot. He was a good-looking guy. He had these male and female friends in his dormitory. So the first thing we had to do was to decide on what are the indicators of flirtation. So I would always send him back to his dormitory, and then he'd meet with his friends. He came back with 6. I told him 6 is too many. Let's narrow it down. And so we chose 4. Touching, acting witty, primping, that's making yourself look good, and eye contact. Okay, again, touching, acting witty, primping, and eye contact. Now, what's interesting is that you can't measure any of these. You can observe them, but you can't measure them. I'm not familiar with a primping meter. Okay? And that was different already, because in all the engineering applications of fuzzy logic, you could measure the signals that you were using. Here, you couldn't measure anything. So what we did is we put things on a scale of 0 to 10, which is what psychologists do. We were flying literally by the seat of our pants. So what we had to do is we had to granulate each of these indicators, that we had to come up with names for some terms. So how many terms do you use? We decided on 5. And he came up with these names, again in consultation: none at all, hardly, a bit, a pretty good amount, and a lot. I wouldn't necessarily use these terms today, but those are the ones that he used. Now we had the next problem. The next problem is you have to locate these terms on the scale. The problem is that everybody's not in agreement where those terms should be located. And so there's uncertainty about the location, and there's overlap between the intervals associated with those. Okay? So, let's see where I am. Okay, so, oh yeah. Okay, so I said we try to locate these on the scale, no complete agreement, and we have sort of a mantra. The mantra is words mean different things to different people. Okay. So we had a huge problem in modeling the words using a fuzzy set that couldn't account for linguistic uncertainty. The standard fuzzy set can't do it. So then what we did is we created very simple rules. Now, I'll never forget this. I was working also with a couple of psychologists here in Annenberg in the School of Psychology, Lynn Miller and Sheila Murphy. Okay? And I told them, I said, well, you know, we have these 4 indicators, so we're going to create rules that have, you know, if eye contact is this, and primping is that, and touching is this. And they said, what, are you crazy? He said, you can't ask people those kinds of questions. Humans can barely correlate 2 things. You go past that, it's impossible. They'll never be able to answer the questions. And that basically they're really good at, you know, picking up one cue and independently another one. Maybe they can cross-correlate, but even that's really difficult to do. So we asked the people, the students, questions like if touching is a bit and eye contact is a pretty good amount, then flirtation is. And again, Matt's friends chose one of the words. And now here we came to another problem. Obviously, there wasn't complete agreement. Instead of getting a single consequence for a rule, we had a histogram of consequence. And again, we didn't know what to do with this stuff using standard fuzzy logic. Another thing is that the answers that we got to the rules were very different for the guys and the gals. Now, you all know, guys, touching goes a long way. But for gals, it's a different thing. Okay? So we needed 2 kinds of advisors, you might say. One for the gals, one for the guys. So that led to a question, a long story to get to a question. But the question was, is there another kind of fuzzy set that can model the kinds of uncertainties that we encountered in really a frivolous application? It was a lot of fun. And the answer turned out to be yes. Mainly type 2 fuzzy sets could do it because they allow you to model linguistic uncertainty. And so the report, actually, that I have on my website is this one here. Anyone who wants to get a fun introduction to fuzzy logic, you can download that on my website. My granddaughter liked this. She was like 14. So now this brings me to my last question. And that question was motivated by a 1996 paper published by Professor Zadi. And the title of that paper was Fuzzy Logic Equals Computing with Words. What the heck is computing with words? Okay, so I prepared a couple of slides. It's a methodology in which the objects of computations are words and propositions drawn from a natural language. It's inspired by the remarkable human capability to perform a wide variety of physical and mental tasks without any measurements and any computations. We do it all the time. And it may have an important bearing on how humans make perception-based rational decisions in an environment of imprecision, uncertainty, and partial truth. And Zadi didn't mean that computers would actually compute using words. Okay? What he meant is that computers would be activated by words. They would go through their things, transform, solve problems, and then the result would be converted back into words. So words in, words out. And that fuzzy sets would be the mathematics that would let you do this, because they could capture linguistic uncertainty. So after reading his paper, again, fuzzy logic equals computing with words, this reminded me of a song. Is that all there is? And this was sung by Peggy Lee in the 1960s. And why I'm putting up this, and is that all there is because when you see a title like Fuzzy Logic equals computing with words, you get the impression that the problem's solved. What's left to do? He said fuzzy logic equals computing with words. Well, it turns out that was far from the truth. That was an idea that he was throwing out, and he's very good at throwing out these ideas. And so that led to the last question, technical question that I want to mention today, and that question was, how do you actually implement this computing with words paradigm? So my students and I worked, another decade goes by, on an implementation, something that we call the perceptual computer. Perceptual computer has three components: the encoder, the engine, and the decoder. Those in communications will recognize that I'm using terminology that is familiar to communications. Professor Zadi uses terms, I have to say, they're hard to say. Precisiation, depreciation. I can barely get that out of my mouth. so I use encoding. So encoder transforms a word into a mathematical model. We use interval type 2 fuzzy sets because they let us capture words mean different things to different people. And there's another slogan. Words have to mean similar things to different people. If that's not true, then you're not communicating. So they mean different, but they also have to mean similar. In terms of intervals of numbers, if your interval is here for a word and mine is there, man, you're not communicating at all. If they overlap somehow, then you're communicating to different degrees. So the big problem or challenge was, how do you collect data about words from a group of subjects and turn that into one of these fuzzy stuff models? We developed a number of methods, each one extracting more and more information from the data. The engine solves some kind of a problem. The solution may be formulated as a set of rules, like in the social judgment. It may even be a linguistic kind of an average. So my student Don Wu invented something that we call the linguistic weighted average. People find it very difficult to evaluate things using numbers. Should it be a 6, a 6.1, a 5.9? On the other hand, they like to use words. And so you can let the evaluation of something be done in terms of words, and the weighting also be done in terms of words. Now, this is an expressive formula. Okay, the math for getting the fuzzy set on the left-hand side can be done. But at a high level, everything can be done in terms of words. And finally, getting back to the perceptual computer, the output of that engine gets mapped back into a word or a judgment. Okay? And we call that decoding. So that actually, so the perceptual computer, in essence, lets you have words in and gives you words out. And there's a lot of interesting problems that have to be solved in order to implement that. So that brings me to the end of the technical questions. So I just want to take a few minutes to mention that during my 50-plus year career, I've authored or co-authored some research monographs. There were 2 on deconvolution and 3 having to do with fuzzy sets. The one on the left is a textbook, the other 2 are research monographs. I've also authored 6 or 7 other books. So I want to focus on a non-technical question having to do with writing books. So here's the question: why do I want to write a book? I know there are faculty who've written books, and that's an interesting question. I don't know whether you asked yourself that question. I don't think I actually did this when I was doing it, but after 50 years, you sort of step back and you ask these kinds of questions. So I don't really have a totally satisfactory answer to that question, but what I can tell you, though, is that there's some sort of pressure that builds up inside of me to write, and then I just have to do it. I don't know, other people who've written this book, you sort of get this feeling that you can see a picture and you have to paint that picture. And that results in the book, and that's also happened in writing some tutorial articles. I know Bob has written a very famous one on spread spectrum communications. So to me, these books and tutorials represent what I'll call the symphonies of my works. And how sneaky I'm connecting back to Ode to Joy. Okay? And so they're my odes to joy. Okay? What I want to do now, this is my last slide. And, just a few minutes, but it's very inspiring. Pretty good, huh? That's arguably from the greatest symphony ever written, Beethoven's Ninth. He must have heard me. So, yeah, I wish I could say that that's what I heard each time I experienced the joy of research. Maybe you hear it as well. So that's why I called the title of this Ode to Joy of Research. So finally, in conclusion, my more than 50 plus years of research, 40 plus at USC, have led to lots of questions and answers as well as the joyous moments. So thanks for listening to me as I've taken you down memory lane, so to speak, and thanks to the Main Shea Institute for giving me the opportunity. Thank you.